All right, well, welcome to our recording for section 6.4. So this is going to be our last section in chapter 6. This chapter is all about power series. The first section introduced power series. The second section talked about how to build new power series from existing power series. And then the third section introduced the important Taylor and Maclaurin formulas for constructing general power series and also specifically power series centered at zero. This last section doesn't really introduce any new ideas per se. It just gives us an opportunity to go a little deeper with some things we touched on earlier. So let's go ahead and have a look at our outline. Alright, so outline for section 6.4. In this section, we'll use the differentiation and integration of power series to solve problems that would have been previously inaccessible to us. Alright, so really get to see, unintended irony, but the power of power series. And we're going to start by looking at a couple of examples in the book, and then I have a physics problem that is similar to an example in the book, but gives a little more background as to where that sort of thing might come from. So let's go ahead and have a look at 211 here. This is the homework set for section 6.4. So in 211, we're given this function big F of x equals tan inverse of x. Okay. Our goal is to construct a power series for it by using the fact that it's fairly easy to build a power series for its derivative. Okay, the derivative of tangent inverse of x is 1 over 1 plus x squared. We usually use that relationship in the other direction as an integration formula, as in like the integral of 1 over 1 plus x squared is tangent inverse of x. Okay, but here we're going to use the fact that 1 over 1 plus x squared is the derivative of tangent inverse x, build a power series for that derivative, and they've actually shown us what that would be, but we'll talk through a little bit about where that would come from. Okay, just as a quick review. And then we'll use that power series to build one for the original function that we're interested in, big F of x equals tan inverse of x. Now notice that they're referring to big F of x as the definite integral from 0 to x of little f of t dt. Let's talk for just a second about why they're doing that. Okay, so let's go ahead and look at our paper here. Aha. So here's what the book gave us. Okay, now remember they said that big F of x, which is really tan inverse of x, could be thought of as the definite integral from 0 to x of 1 over 1 plus t squared dt. So if we just apply the fundamental theorem, we know that the antiderivative of 1 over 1 plus t squared is our tan inverse of t. But then since it's a definite integral, we're going to plug in x and plug in 0. And that's going to give us tan inverse of x minus tan inverse of 0. But tan inverse of 0 is 0. Okay, so really that just knocks down to tan inverse of x. Okay, now why did they choose to put it that way? Well, let's think about it coming from the other direction. Okay, let's start with this derivative with t as the input variable. Let's kind of recap how they got. The book gave us that this is the power series expansion of our derivative function here, but let's just review how they got that. So when I write this function down, I can see that it has a form pretty similar to the form that gives us the sum of a convergent geometric series. Okay, so if we've got a geometric series of the form a times r to the n, where n goes from 0 to infinity like that. Okay, as long as r is between -1 and 1, that geometric series would converge to a over 1 plus r squared. Okay, now it doesn't quite match up. I need to tweak it just a little. I can always recharacterize addition as subtracting a negative. Okay, now if I put my function in this form, 1 over 1 minus negative t squared, then I can identify a as being the 1 and r as being the negative t squared. Okay, and if I can make those associations, then I can make the jump and say, alright, this fraction should be equal to a power series where n goes from 0 to infinity of 1 times, alright, 1 is my a, and my r is this negative t squared, so that needs to be raised to the n. Now we can always think of this negative as a factor of -1 and distribute the n to that -1. Okay, and if we do that, then we would get a series that looks like this. I'm not going to bother writing this 1 anymore, but I've got a -1 to the n and a t squared to the n. But of course, if t is raised to 2 and then the whole thing is raised to n, the 2 and the n can multiply. Okay, and this is exactly how the book got what it gave us right up here. Okay, but now, so let me write this just to kind of summarize what we've got here. Okay, so f of t equals sum from n equals 0 to infinity, -1 to the n times t to the 2n. Okay, very good there. Now, that's the derivative of the function we want, so it would make sense to take an antiderivative. Now, if I take a general antiderivative, okay, if I take a general antiderivative, then let me see. These terms are all just a constant times t to a power. So I'm going to leave a little space on purpose here. I want to take those powers and increase them by 1. So I'll make that t to the 2n plus 1. That plus 1 is not directly on n. It's on the whole quantity 2n. Now, of course, this coefficient out front is still there. But we also want to divide by this new power. Okay, so we're just using one of the most basic antiderivative rules, the power rule for antiderivatives. But there's one more pretty basic antiderivative rule, and that's when you compute an antiderivative, you get a constant of integration, which is why I left a little space. Now, check this out. I've got a c, and if I start writing these out, n starts at 0, so the power of t starts at 1. So I'm going to get a 1 times t to the 1 over 1. So I'm going to get a t, and then if I keep going, I would get a minus t cubed over 3 and plus t to the 5 over 5 and minus t to the 7 over 7 and so on. But here's the thing I want you to see. Okay, this antiderivative must be it must be what we're going to use for our arctan, but this is a general antiderivative, not a specific antiderivative. To make it a specific antiderivative like arctan, we need to figure out what c should be. Okay, so let's go ahead and say we want this to be tan inverse of t there. Okay, to nail down what c should be to get that specific antiderivative, we could plug 0 in for t, and the reason that's useful is that it makes all these terms disappear. So if I do that, then I would get that tan inverse of 0 equals just c, because all those get zeroed out. Now, of course, tan inverse is 0, so 0 equals c. So since 0 equals c, we can kind of leave that off and say, all right, our final answer, big F of x, which is tan inverse of x, would just be the rest of these terms. So x minus x cubed over 3 minus plus x to the 5 over 5, and then so on. So of course that would be the series n goes from 0 to infinity, just pretty much as we had it written up here, but with an x instead of a t. So negative 1 to the n times x to the 2n plus 1 divided by my 2n plus 1. Now, let me go back and just briefly mention, so there's our answer. This is what the problem is looking for. Let me go back and just briefly mention that by characterizing f of x as the definite integral from 0 to x of 1 over 1 plus t squared dt, they were basically giving us the opportunity to subtract off that tan inverse of 0, which is our c. Okay, so presumably this had the c in it, but then this subtracts the c off. Okay, now we have tan inverse of x without that extra c. So, I mean, that's why they chose to write it that way. Okay, but basically the idea just boils down to, I know the power series for the derivative, so I need to take an antiderivative and then figure out what the plus c is. All right. Let's do a similar problem. Okay, let's do problem, this one is 215 in the book. So let's go back and have a quick look at that. Similar type problem. They want us to build a power series for a function, big F of x, okay, equal to the antiderivative, or actually the definite integral from 0 to x of cosine of square root of t dt. Now, let me tell you what's a little different about this one. In that last problem, we knew what big F of x was. It was arctan of x. So we could have actually built the power series directly if we'd wanted to. Okay, we could have used the Taylor formula and started computing derivatives of arctan and built the coefficients one at a time. We could have done it directly. Okay, we wouldn't have had to appeal to the derivative. Okay, but in this case, I don't know what the antiderivative of cosine of square root of t is. Okay, this isn't really a type of integral that we've ever tried to figure out. Okay, none of the integration methods that we've used previously in the course would really work on this one. Not the substitution, not the integration by parts. So I really can't use the fundamental theorem of calculus directly, but I can use it indirectly. Okay, here's how I can use it indirectly. Let's go back to our paper and write down what they gave us here. So they gave us this, that big F of x is a definite integral from 0 to x of cosine of square root of t dt. Now, the first form of the fundamental theorem of calculus, the one we don't use real often, says that if I have a function that's defined as a definite integral of another function, in this case cosine of square root of t, then if I take the derivative of the function that is an integral, then essentially the derivative cancels out the integral, and I'm just left with the function on the inside of the integral with x dropped into it. So this is the function that we want to build a power series for, but we don't even know how to write this function without an integral. It's not an elementary function. Okay, it's the integral of something that's a transcendental function to start with, and we just don't always know what to do with that. But even though I can't write it without an integral, I could write it as a power series if I first construct a power series for its derivative. Now, I know that a power series for cosine of x, because I've built it previously, looks like a sum from n equals 0 to infinity of -1 to the n times x to the 2n over 2n factorial. Okay, and we saw in section 6.2 that if we already know the power series for a function and we want to construct a power series that's basically that same function but with a power of x plugged into it, we can just plug that power of x into the power series of the known function. So I can say, well, that guy, okay, the cosine of square root of x, that guy as a power series would have to be the sum from n equals 0 to infinity of -1 to the n, and then just where that x is, drop in a square root of x, so square root of x to the 2n over 2n factorial. And of course there's a little simplifying we can do there because we have a power and a root that cancel. So we can say that cosine of square root x equals sum from n equals 0 to infinity -1 to the n of just x to the n over 2n factorial. And now if I want to get my original function, okay, my f of x, okay, then I can just take an antiderivative here. Okay, so I can say f of x would have to be the antiderivative of this thing. Now again, I'm going to leave a space here because there's a plus c that comes with integration. I'm going to have to work that out. But it'll be a sum from n equals 0 to infinity, -1 to the n, times x to the n plus 1, and then I need to divide by that new power, so n plus 1, times my 2n factorial. Now, to work out what that c is, I need to decide what f of 0 is. So f of 0, well, let me see, f of 0, I can appeal back up here. F of 0 would be an integral from 0 to 0 of cosine of square root of t dt. But any integral that begins and ends on the same at the same value of the variable of integration is 0. So 0 equals c plus, well, let me see, if n starts at 0, then my first term is x to the 1. So all of these terms, when I plug 0 in for x, would disappear. So 0 equals c plus a bunch of terms that zero out. So c equals 0. And then we can say, for our final answer, f of x equals just this sum from n equals 0 to infinity, -1 to the n, x to the n plus 1 over n plus 1 2n factorial. Alright, now I do want to point out to you that it isn't always the case that f of 0 is 0. Sometimes f of 0 is something else, and so c doesn't have to be 0. So you might wind up with a constant that if c was 2, then you would have 2 plus an infinite sum. And that's how you would write your answer, 2 plus the sum in sigma notation. Okay. All right, well, let's go back to our outline and look at one more problem. Okay, so we've already done a couple of examples of one of the major problem types of section 6.4, which is basically integrating a known power series to create a new power series. And in particular, what we've seen is that sometimes this can allow us to find power series forms of antiderivatives that we wouldn't really have any other way of going after. Okay. Now, the other major problem type that's in this section that hasn't really been emphasized before is problems where we use power series to solve differential equations. Now, I have done that a couple times as a means of constructing power series, but I wasn't really very explicit about what I was doing, okay, because I really wanted to focus on building the power series, okay. But I want to take a moment to be explicit about how power series can be used as a tool to solve differential equations, and not just simple ones like I've done already, but even somewhat more complicated ones. So some of you will eventually take a course on differential equations, and the problem I've chosen is actually a problem that's typical of an introductory course on differential equations, but it results in the kind of differential equation that the book is having you do in this section. So I thought this would be a nice way to give a little context. So this problem is about an electrical circuit, and we're going to keep the numbers as simple as possible. So we're going to say that this circuit has an inductor with an inductance of 1 Henry, a resistor with a resistance of 1 ohm, and a capacitor with a capacitance of 1 farad. Alright, now if this were a differential equations class or a physics or an engineering class, I would go through Kirchhoff's laws and talk about how we would use them to translate this information into a differential equation. But for now, I think that would take us too far afield. So I'll just suffice it to say that using Kirchhoff's laws, we can translate the information in that first paragraph into a differential equation. Okay. Here, Y represents the charge on the capacitor. So to satisfy all of those conditions, our differential equation, we basically, those numbers, though we're all ones, okay, become coefficients here. That 1 Henry becomes a coefficient of 1 on the second derivative of Y, and that 1 ohm becomes a coefficient on the first derivative of Y, and that 1 farad of capacitance becomes a coefficient actually it's the reciprocal of the number of farads that becomes the coefficient of Y. Okay, but suffice it to say that in order to find a formula for the charge on the capacitor as a function of time, we could solve this differential equation. Okay, now you've solved differential equations in Calc 1, okay, but they were somewhat simpler than this. Technically, anytime you took an antiderivative, you were solving a first order differential equation. If I ask you to find the antiderivative of x squared, I'm really saying solve the differential equation y prime equals x squared. And you would tell me, well, it's y equals x cubed over 3 plus c. Okay. And you even did some second order differential equations where you started with a second derivative and integrated twice. So I'm talking about Calc 1 here. So you solved both first and second order differential equations in Calc 1, but you probably didn't solve a differential equation that had the original function related to both its first derivative and its second derivative. That's a little trickier, but it is possible to tackle this with power series. Now we do need a little more information. We need some initial information about the state of the system. So I've provided that here as well. Okay, so we're going to go ahead and say the capacitor initially has 1 coulomb of charge on it, and initially there's no current in the system. Okay, so initially would be when time, so that would be our input variable, time is 0. So if initially we have 1 coulomb of charge, then y of 0 would be 1. Okay, now current is the rate of change of the charge. We usually think of it as flow rate, but you could think of it as the rate of change of the charge. So current is the derivative of the charge. So if there's initially no current in the system, then y prime of 0 is 0. Now we've got enough information to get started. Okay, we're going to tackle this differential equation by assuming that there's a Maclaurin series. Okay, we're going to assume that there's a Maclaurin series that converges to this unknown charge function that we're trying to find. Okay, so we're assuming that there is a power series of the form infinite sum from n equals 0 to infinity of a sub n times x to the n that would be equal to this charge function. Okay, now we can be relatively sure that there is such a thing, because even not knowing much about the charge, I would expect it to be a continuous function. Okay, and continuous functions can almost always be represented as Maclaurin series. Okay, by continuous I mean the charge would not instantaneously jump from 1 coulomb to 2 coulombs. It might do it very, very quickly, but it can't do it instantaneously. It would take some amount of time, which means if I was tracking charge as a curve, the curve wouldn't break. Okay, it might rise steeply, but it wouldn't just jump. Okay, there wouldn't be a break in the curve. Now the trick to this is, assuming that there is such a Maclaurin power series, we need to figure out what these coefficients are. If we knew what y was, then we could build these coefficients by taking the derivatives of y. That's what those formulas we learned in the last section were about. But here we don't know what y is. We're trying to find y. Okay, so we're going to find our coefficients not by knowing what y is, but by knowing how y relates to its first derivative and its second derivative. We're going to use the differential equation itself to construct the coefficients of our Maclaurin series. Okay, so let's talk about what that looks like. Alright, so back to our paper here. So we're assuming that y looks like some series of the form a constant plus a constant times x plus a constant times x squared plus a constant times x cubed and a constant times x to the 4 and a constant times x to the 5. Okay, and we're going to figure out what those constants are, but until then we'll just generically call them a1, a2, a0, a3, and so on. Okay, now there's infinitely many series to the term, but we're only going to use a finite number of terms to approximate our charge function. Okay, the problem actually said to use the 5th degree Maclaurin polynomial. So if we can figure out our coefficients up to a5, then we'll be ready to do our approximation. Now, the differential equation tells me how y, y prime, and y double prime are related. Okay, basically it tells me that their sum has got to be 0. So let's take the derivative and the second derivative of our generic Maclaurin series that we don't really know at all, but we know it has this form. So when I take the derivative, a sub 0 disappears. This term becomes a constant term. So a1x becomes a1. In this term, we bring the 2 down. So I get plus 2 a2x. We bring the 3 down and I get plus 3 a3x squared. Now notice I'm being careful to line up like terms, constant terms, degree 1 terms, degree 2 terms. I'm doing that on purpose. Let me see, I bring a 4 down, I get a plus 4, a sub 4 x to the 3, and a 5, a sub 5 x to the 4. And then the next term that I didn't write would have been a sub 6 times x to the 6. So if I bring down the 6 in that term, I would get 6a sub 6 x to the 5, and then so on. Now I'm just going to do that again. Okay, so if I differentiate my derivative to get the second derivative, the a sub 1 goes away, and this term becomes my constant term, 2a sub 2. And then here I've got to bring down the 2, so 2 times 3 is 6, a sub 3x. Alright, notice again I'm keeping the x's lined up as well as I can. Now, differentiating the next term, I'm going to have 12, a sub 4x squared. Okay, and then it looks like it'll be 20, a sub 5x cubed. And then bringing that 5 down, I would have 30, a sub 6 x to the 4. And the next term that I didn't write would have looked like 7, a sub 7 x to the 6. And if I differentiate that one, I would get 42, a sub 7 x to the 5. And for some reason I wrote 2 a's there. Alright, that's enough. That is enough for us to get going here. Now, I'm going to use the differential equation itself. So remember, our differential equation is that y double prime plus y prime plus y equals 0. I'm also going to use our initial conditions. Y of 0 was 1, and y prime of 0 was 0. Let me start by applying this first initial condition to the original power series. If y of 0 equals 1, well, when I plug 0 in, everything disappears except that first term. So that means a sub 0 is 1. Okay, so y of 0 equals 1 implies that a sub 0 equals 1. And then also, since I know that y prime of 0 is 0, okay, I can go to the derivative of my power series and say, hey, when I plug 0 in, everything disappears except the a sub 1. So a sub 1 is 0. Okay, now, to build more coefficients, I need to start using my differential equation. Okay, and I'm going to use the fact that for these three series to add up to 0, their constant terms would have to add up to 0, their x terms would have to add up to 0, their x squared terms would have to add up to 0. So I can say a0 plus a1 plus 2a2 got to be 0. a0 plus a1 plus 2a2, that's got to be 0. But I know that a0 is 1 and a1 is 0, so if I put a 1 there and solve for a2, I would get negative 1/2. So a2 is negative 1/2. So now I know the first three coefficients. Alright, now I used the fact that the constants had to add up to 0, but also the coefficients of the x terms have to add up to 0. So a1 plus 2a2 plus 6a3 got to be 0. So a1 plus 2a2 plus 6a3 got to be 0. So let me think. a1 is 0, that's easy. A2 is negative 1/2. Multiply that by 2, I get negative 1. Now if you got to write more out, that's okay. Negative 1 comes to the other side, becomes a 1. I divide by 6. It looks like A sub 3 is 1 over 6, or maybe 1 over 3 factorial. Alright, well, remember our goal was to get out to A sub 5. And then that'll be enough terms for our approximation. Okay, so a couple more of these and we'll be there. Alright, so we already used the first two sets of terms. Now, let's use the x squared terms. A2 plus 3a3 plus 12a4, that's got to be equal to 0 to satisfy our differential equation. So, A2 plus 3a3 plus 12a4 must be equal to 0. Let me see, A2 is negative 1/2. A3 is 1/6. 3 times 1/6 is positive 1/2. Oh, so these two terms actually cancel out. And if 12a4 equals 0, then a4 has to equal 0. Yeah, so there is no degree 4 term in this power series. No biggie. Alright, let's go one more. So, using the x cubed terms, I can see that a3 plus 4a4 plus 12a5, those would all have to add up to 0 for these three functions to add up to 0 and satisfy the differential equation. So, one more time, a3 plus 4a4 plus 20a5, that's got to be 0. A3 is 1/6. A4 is 0, so we can forget that. So if I bring the 1/6 over, it'd be negative 1/6. Divide that by 20. So A sub 5 is negative 1 over 120. Now notice my coefficients are shrinking pretty quick. It's definitely something I hope to see, because it should mean then that my series is converging pretty quick. Okay. Now part A was just to build the 5th degree Maclaurin polynomial. So we'll call that P sub 5. P sub 5 of x. Well, let me see. A sub 0 is 1. That's our constant term. Looks like we have no x term. Here's the coefficient of x squared and x cubed. So if I start writing this stuff out, I'm going to have 1 minus 1/2 x squared plus 1/6 x cubed. There was no 4th degree term. Minus 1 over 120 x to the 5. So there's our 5th degree Maclaurin polynomial that is an approximation for our charge function. Alright, so that answers question A. Let's have a look at question B. Okay, we did it. We found the 5th degree Maclaurin polynomial for y. Now in part B it says use the answer to part A to approximate the charge on the capacitor after 1 second. Okay, so here x is our seconds. So for part B, what we really want to know is y of 1, the charge after 1 second. But y of 1 would be approximately P5 of 1, which would be 1 minus 1/2 plus 1/6 minus 1 over 120. Well, it looks like a little calculator problem. So, calculator, tell me please, how much charge do we have after 1 second? 1 minus 1/2 plus 1/6 minus 1 over 120. Well, remember we started with 1 coulomb, and it looks like we've dropped off to 0.658333. It looks like the 3's just repeat after that. And that's coulombs. So if we wanted, we could put a big C there for coulomb. Okay. Now, that's an approximation based on a polynomial that is an approximation of a function that we are assuming can be written as an infinite power series. But then the question is, how good is the approximation? Well, in this case, I can actually get an idea of how good it is because my polynomial, when I plug 1 in it, becomes the partial sum of an alternating series. So if I can just figure out what the next term of that series is, the next term would be an upper bound. So this is part C, find an upper bound on my error. If I can find the next term of this alternating series, that'll give me my upper bound. To get that next term, I'm going to have to come all the way back up here and solve one more equation so that I can see what a sub 6 is. Okay, a sub 6 will give me my next term. Okay. Alright, so it looks like a sub 4 plus 5a sub 5 plus 30a sub 6. All of that got to equal 0. Now remember, a sub 4 is 0, and there's a sub 5. So 5 over 120, and remember a sub 5 is negative, so negative 5 over 120 plus 30 a sub 6 equals 0. Well, let me see. That would imply that a sub 6 equals positive 5 over 120 times 30. Let me ask my calculator what that is. 5 divided by 120 divided by 30 is 0.00138. Okay, well, that right there, that would be my next term. Okay, my sixth term. I mean, technically my next term would be that times x to the 6, but since we're plugging in 1 for x, the next term of this alternating series would be that number, which means that number is an upper bound on my error. So this is my answer. So my approximation for the charge after 1 second, it's only off by at most a little over 1/1000th of a coulomb, which is not a bad error. Now, if I wanted to make my approximation better, I could add this number to that sum and then find the next term, and the next term, which would be even smaller, would give me an upper bound on the error of that even better approximation. Okay. So this is something we definitely would not have been able to do with techniques we've learned previously. We would not have been able to solve a differential equation this complex, and therefore we really wouldn't have been able to solve this little electrical engineering problem. Now, there is actually a way to get the answer without having to directly use power series. Okay, the answer is actually the function that we're looking for. I worked it out earlier. It was e to the negative 1/2 x times cosine of square root of 3 over 2x plus 1 over square root of 3 sine of square root of 3 over 2x. There is a way to get that as our answer, which you would learn in a differential equations class. But even doing that, requires you to have Euler's formula. And we showed a few sections ago that Euler's formula comes from power series. Okay, so one way or the other, you're using power series in this to solve this problem, even if you're not using them quite as explicitly as we did right here. All right. Well, you know what? That's actually everything I wanted to go over in this section. This is really more practice of things we've already done, but maybe a little more, maybe a little more complicated than some examples we've already done. Okay, but we've previously built power series from scratch by using derivatives. Okay, we were just a little more explicit about the fact that we're solving a differential equation. Okay, and we'd previously integrated power series to get new power series, but we maybe hadn't explicitly done it to get an antiderivative that we had no other way of getting. So, some neat little applications that tie power series back to problems, both problems that we were studying earlier in this class, like how do you find the antiderivative of a function, and problems that a lot of you will study in future classes, like how do you solve a second order linear homogeneous differential equation. Okay, so I think that's everything I want to do for this section. So let me go ahead and flip my view back here, just so I can say goodbye to you. I mean, I took time to shave just for this video, so I want you guys to see that I look good for you, nice and professional. Even put on a nice shirt. Okay, just so I can feel like I'm working in my office. Although I gotta tell you, my office isn't nearly this comfortable. I know that this business with the quarantine is no joke. It's meant bad stuff for a lot of people. But looking on the bright side, it is actually kind of nice to work from home. I mean, there are benefits. For example, I'm about to go get some more tea. I don't even have tea at work. I just have coffee. I'm trying to cut back on that. I know there's caffeine in tea too, but maybe not as much. All right. Well, listen, I hope you're all doing well. I hope you're staying safe and healthy. And as always, if you've got questions about anything, let me know. I'd be glad to get on Zoom and go over stuff with you. Take care, everybody.